Hey, we're going to graph some logarithmic functions with transformations. And before we do, I'm going to quickly remind you of some things that you should already know before this video. You need to understand log parent functions, and there's really two shapes that you would encounter with a log parent function. So a log parent function always looks like y equals log with some base of just x as the argument, okay? Any arithmetic that occurs on this would be a transformation. And so if your base b is greater than 1, then your log function will go through the ordered pair 1, 0 and have an asymptote on the x-axis at y equals, have an asymptote on the y-axis, which is the line x equals 0, and the graph would increase from right to left but get slower and slower, and as it moves left it's going to get closer and closer to that asymptote as it goes down. If your base b is less than 1 but positive, we're only going to look at positive bases. Well, the good news is you still are going to go through the ordered pair 1, 0 and still have an asymptote where x equals 0, but now it's going to grow in the negative direction more and more slowly, and as it goes to the left it's going to get closer and closer to this asymptote. Sorry, that's a bit hard for me to draw. That should be smooth right there. So those are your log parent functions. Let's review transformations. Y transformations, they occur outside the parent. This is arithmetic outside the parent function. And the order and the operations are what you see, what you expect. X transformations occur where x is, and in a log function that's in the argument. They occur inside the parent where x is. So in a log function that's in the argument. And the order and operations, this is the tricky part of all of the transformations. The order and the operations are inversed. So you inverse the order and you inverse the operations from what you see. Okay, you should know all that. Let's do some examples. And let's put a grid on here that we can use. Let's say we want to graph f of x equals log base 3 of negative x plus 4. And so our parent function here is y equals log base 3 of just x. And so we need to generate the xy table for that parent function, or generate its graph, and then we'll do the transformations. For the log parent functions, the inputs are powers of your base, so powers of 3. 3 to the 0 power is 1. I always like to start there, so the exponent's 0. 3 to the first power is 3. 3 to the second power is 9. 3 to the negative 1 power is 1/3, and 3 to the negative 2 power is 1/9. Notice that the inputs here are the powers of 3 and the outputs are the exponents. Okay, this is the inverse of an exponential function. It's the inverse of y equals 3 to the x, which hopefully you're familiar with. All right, now what are the transformations? Well, we have no y transformations because there's no arithmetic outside the log. So there's no y transformations. The x transformations are inverse in order and operation. So we can see we've got times negative 1 and add 4. So our x transformations are in reverse order. So start with the last operation plus 4 and inverse it. So it's going to be -4. So we're going to shift left 4. That's our first one. And then our first operation was times -1, so we inverse that to divide by -1 for our second x transformation. This reflects over the y-axis, a horizontal reflection left to right over the y-axis. So we need to do both of these transformations to the x column in that order. Now, what did I forget with my parent function that's crucial, especially for beginners? I'm really familiar with log functions, as I should be, so I don't think I would forget. But we can see that the x values here are getting really close to 0. So we actually have an asymptote at x equals 0, which I'm going to label in my x column so that I make sure to apply the x transformations to this x equation. So the first thing I'll do is subtract 4 from my x values and get a new xy table. Now we can see we have new x values, including the asymptote shifted left 4 units, so it's now x equals -4. The y values don't change, so I'm not going to write those down again just in the interest of time. However, our reference point 1, 0 is now the reference point -3, 0. It moved left 4 units. The rest of the y values are the same as they were before. Now I need to do my second x transformation, which is divide all of my x values by, excuse me, divide all of these guys by -1. So they're just going to be positive, and this will be our final xy table. So I'll write in all the x and the y values. So all my x values have changed sign when I divided by -1. My y values are unchanged because there were no y transformations. Notice my asymptote now is x equals +4, and my reference point is 3, 0. Those are good places to start when you graph. This is our final xy table for the function that we wanted to graph. So if we plot this out, I got a reference point at 3, 0. I've got an asymptote at x equals +4. And let's plot the integer order pair. So 1, 1 is there. -5, 2 is up here. So this is our growth side. It's going to grow slowly to the left. And I could plot the other 2 points, but we know how it's going to behave. It's got to get closer and closer to this asymptote. So I'll just draw that in. But if you plotted these 2 points, x is 3 2/3 right here, y is -1, and then 3 8/9, -2 is down here, even closer to the asymptote. And you can see the behavior of the transformed function. All right, let's try another one. In this case, let's graph -2 times log base 2 of x. The parent here is, if I strip away the arithmetic and just have a log of x, it's going to be y equals log base 2 of x. And so I'll generate my xy table for my parent, where the x values are powers of 2. So 2 to the 0 is 1, 2 to the first is 2, 2 to the second is 4, and then the reciprocals of those, 2 to the -1 is 1/2, 2 to the -2 is 1/4. All right, and now let's go ahead and find our transformations. Let's also put our asymptote in, which is x equals 0 for our log functions, and our reference point is the order pair 1, 0. Now we have no x transformations here. There's no arithmetic happening in the argument with x, so no x transformations. The y transformations, remember you do not inverse these, it's just times -2, which actually does 2 things. Because it's multiplying by a negative, it's going to reflect over the x-axis. And because it's multiplying by 2, it's going to be a vertical stretch by a factor of 2. So it's going to flip over and stretch out vertically. Now, all of that's accomplished with one arithmetic operation, multiplying by -2. So all I have to do is go to my y column and multiply these guys by -2. And I'll get my new xy table, and that will be it. So when I multiply my y values by -2, they all switch sign and double. Our reference point remained at 1, 0, right? There were no shifts or anything, just stretching and reflecting. And my asymptote remained at x equals 0. So I'm going to start by plotting those because this is my final xy table for my transformed function. 1, 0 is here, x equals 0 is on the y-axis. This sort of establishes the boundary of my curve. And then let's plot the easy points 2, -2, and 4, -4. You can see these points are twice as far from the x-axis as the parent function. This is our growth side, so to the right I'm going to grow in the negative direction like this, slower and slower. And obviously on the other side I have to keep getting closer and closer to my asymptote. And you could see that if you wanted to plot these points, but we don't need to because we understand log functions. So that's one where you've got y transformations and no x transformations. We did one where you had x transformations and no y transformations. Now let's do one that's got both. All right, so we've got f of x equals 4 plus log base 1/3 of the argument x over 2. So we're going to have one y transformation, which will be adding 4, and we'll have one x transformation, which is the inverse of dividing by 2, so multiply by 2. But first we need our parent graph, which I'll catalog with the table. Our parent function is log base 1/3 of just x. So the inputs, the x values for this function will be powers of 1/3. 1/3 to the 0 is 1. 1/3 to the first is 1/3. 1/3 to the second is 1/9. And then I'll look at my negative exponents. 1/3 to the -1 is 3. And 1/3 to the -2 is 9. And I could keep going. And we can see that the asymptote for this guy is x equals 0 with a reference point of 1, 0. I've already mentioned the transformations now. I know I'm going to add 4 on my y values. I'm going to shift it up 4 units. And I'm going to multiply my x values by 2. I can do these concurrently because the x and y values are independent. That's going to be a horizontal stretch by 2. And I'll generate my new table and we'll be done. So I multiplied all the x values by 2. I added 4 to all the y values. My reference point is now 2, 4. My asymptote is x equals 0. And that's my final xy table. So let's plot it out. Reference point is 2, 4. And my asymptote is at x equals 0. So I know I'll get infinitely close to that on one side. And then let's plot 6, 3. That is over here. And 18, 2 is way off the grid up at 2. So this is going to be our growth side in the negative direction, and it's getting slower. If you imagine that point, even though we can't fit it on the grid, we can understand the behavior. Now, I'll argue that as I move to the left, I have to get infinitely close to the asymptote going up. But let's go ahead and plot the points to see that. If x is 2/3, that's less than 1. So right here, less than 1, y is 5. And then 2/9 is even smaller, comma 6. So we're closer to the asymptote. So we can see that plotting the points also tells us what we expect. And that is how you graph transformed logarithmic functions of various bases, various transformations. The beauty of transformations is they affect every function the same way. So this is our, I don't know how many go-arounds we've had with transformations, but they should definitely be getting easier.